Yeah, welcome back everyone for High Performance Computing, Advanced Scientific Computing. Today we have a practical lecture, our practical lecture 1.1, which builds on our introduction lecture, and we will have a short introduction to C programming and scheduling. And both terms, C programming and scheduling are very important in high performance computing, and I will also make the case for it. So why we talk about C programming. In some forms, you even found Fortran, so interesting languages in high performance computing, and not at all a Java space, for instance. And then we look a little bit into scheduling, what means scheduling of tasks, of jobs, of applications, and why we do this, because also think about that HPC are multi-user systems. But before we go into the material of that lecture, let us a little bit review what we had the last time when we talked about HPC in a more broader sense as a really introduction lecture. We covered a lot of basics for high performance computing. And this surely starts with the lowest parts in the, let's say, hierarchy in terms of a very big system. You would say the smallest parts in it is really the cores, the computing capacity. So we looked a little bit into multi-core processors, the idea of caches, and so on. And they're usually this typical, let's say, multi-core processors. They have very high signal thread performance, and they're incredibly often used in parallel programming and parallel computing. What that means is we want to have different processes, really, where basically an application is running and not anymore just on one core. So we were talking about how we use different cores together and then also across the nodes. And that quickly brings us to something called the message passing interface, because essentially you have two setups. One is essentially for the really large scale system aspect of it, that you would have this kind of idea that you basically have a distributed memory setup. You have an architecture where one processor cannot very quickly basically go to the memory of the other one. So there needs to be a communication network between it. And this network interface enables, of course, to send and receive messages. You see that a little bit here on the right-hand side, where basically then this different processors can really interact with each other and solve a big problem in a cooperative way, which is more or less the idea of why we do parallel computing. Of course, here we have just 5 processes basically in parallel. You can imagine that, of course, when we have a huge amount of processors involved, we come to sometimes 1,000 and so on. And we will make the case for it in the course in later parts also when we talk about real applications. The other part of it is, of course, that you can have this set up a little bit on an OpenMP way programmed, meaning using shared memory. That's also what we discussed the last time. Of course, here you would have different threads because you're still in the realm of one basically chip here, and basically have the chance, of course, to write into the memory and read from memory from the different processors. So this is a setup where still OpenMP shared memory programming is possible. And we heard there's a NUMA and a CC NUMA, a cache coherent way here of basically fake the idea of doing shared memory, but still it's possible to do so from these processors. So basically, when you do shared memory programming, there's not really a send and receive like we would have in distributed memory, but more or less basically writing and reading from memory, which can be tricky. We will learn about this in later lectures, like lecture 6, for instance, when we have OpenMP. Now, of course, today people have basically combined that. We have today very much production systems which have applications where MPI is used across the different nodes and shared memory is within the node. And also this is something we will review in the next lectures more and more. Now, the other part of the lecture was then understanding perhaps a little bit the difference to a so-called many-core system, a many-core processors really that have, let's say, more moderate single thread performance, but very many hundreds of processors. So they are not having a heartbeat as fast as the typical multi-core processor. Here we talk about accelerators, and the reasoning is that they accelerate a lot of programs and libraries today One that we had as an example was a deep learning one, where you have your deep learning network, like a convolutional neural network, for instance, as an example. And we have seen that lots of these ideas are basically lots of matrix multiplication or matrix vector multiplication, and this can be nicely parallel solved. You see here the color encoding, meaning essentially that for the solution of this vector here, by this matrix vector example, all you need is this information from the colors. And then you can imagine it's really nice to break that up in different processors. And that's what we will do. But all of these computing then are inherent, not so complex, right, in order to compute the resulting vector. So in other words, this is a nicely parallel setup and can be very nicely solved in the GPU system. The drawback of a GPU right now from NVIDIA, but also from others, is usually going often via the main memory, basically to fill the device memory. People work on workarounds on this to basically use directly memory interfaces and so on, and messages to other accelerators to use them, for instance, in parallel. But these will be all material of subsequent lectures where we go into it. It's important, however, to think about that, of course, HPC is not anymore used just for modeling simulations these days. We see an example of an earthquake simulation, traditional physics simulation that we had in the first lecture, as an example for big data, where really lots of data sets are generated out of the simulation. Also, HPC is used the opposite way. So once you have big data, let's say satellite images that we discussed in the last lecture for remote sensing here as example, and you want to work with them with different deep learning networks. If you're an autoencoder example, these are convolutional neural networks. This is all not really the big difference here today. Deep learning is there used, and HPC is really needed firstly to compute basically the learning process, which reflects a lot of these matrix vector multiplication, matrix multiplications, really these tensors. But today also we have lots of these hyperparameter to solve. So what optimizers we're going to use, what is basically the best activation functions, how many batches and epochs. So this is an element we also will discuss in one of the lectures, why HPC is needed. In order to find the right idea of these hyperparameters, you have to experiment. Nobody tells you this. So you basically try out many things using RayTune and other tools, which we will have in the lecture, starting from lecture 10 or so, where we look a little bit on AI, basically in the HPC perspective. And then at the end of the last lecture, we really looked a little bit into the future, but we also learned that the future is already there. So quantum computing, often mistakenly thought of being, not really active yet. We have basically shown some examples from quantum annealing, where we in our research group, for instance, already are publishing. It's basically some very important topic and an interesting future topic. And with this, I also encourage you to look into this. You have seen in YouTube, there's a Ute Messan, for instance, lecture from me from a couple of years ago, which already basically is very basic just to understand what qubits is, how you program essentially a quantum annealer. A big space, admittedly, and quantum annealing is just one little fraction on it. There are gate-based approaches, there are basically many of those, but it's an interesting technology, very related to HPC. We saw in Jülich, it's considered basically as one of the modules, right? If you remember, we had the modular supercomputing in the last lectures, and then basically the quantum computer would be almost like an accelerator, like a GPU used for specific problems. And one of the interesting problems to solve with a quantum computer is the optimization of machine learning algorithms, because they all rely on some optimizer. You see here stochastic gradient descent for an example. But basically, these are beautiful problems to solve by quantum annealing. And this will be also an invited lecture in our later parts of the course. But let us come now a little bit to more practical insights. So here it's again a very basic lecture. And of course, I cannot cover C programming as a whole. So this requires training 5 days from morning till evening if you want to be a C expert, if not more time. And here the goal is really think about that we go quickly through the basics, why we want to have basically the C programming, why it's so important for the course. Also to take your anxiety, maybe just looking at the simple C program, and basically thinking about how you really use that in combination with the HPC system, which is quite different from what you perhaps know by compiling Java on your laptop, by compiling maybe even C# applications with some, API or with some developer environment. So here we look a little bit that a HPC system has specific nodes, has specific modules, and we will also, of course, go step by it. Also to show you one important part, which means that you never should use a login node for executing C programs. So I will come to that. And then the second part basically comes to the schedulers on HPC systems. We learned already in the last lecture a little bit more conceptually that these large supercomputers are used by many different multi-users at the same time, right? And at the same time is loaded. So it's, again, not your laptop that is just used by you. So how should the system work if you, let's say, have 1,000 users in parallel? We will talk about this scheduling. And then, of course, you think that the number of cores in the system is limited. So there needs to be someone taking care of looking when is the system free, when it can be used, and basically then also do the quota. So how much can you use it, and so on. So being, in the so-called batch processing mode, we will learn here to have the second part really on scheduling principles. What does it mean to be scheduled, a queue? And with this, we also will understand more and more the difference between a compute and login node, which is very important, also not in getting conflicts with administrators, which I will convey with a message that you never should execute C programs really on login nodes if they are, let's say, computation intensive. The right way to do it is, of course, using so-called scheduler batch scripts or the scheduler Slurm examples that we're going to do on Jötunn to really execute then your C program on the compute nodes. You can always compile usually if it's not taking too long on the login node, but if it comes to the execution, this is usually done on the HPC system. And I show you as a basic how that works. And then, of course, in subsequent assignments in the course, you will also get your hands on and then will understand that much more. So very practical oriented lecture. And with this, you really should come out of this lecture how to use a high performance cluster. So we had Unix in the beginning, we had SSH, which was the access and a little bit of working with a file system. Now we complement these idea practically with the idea of a short compilation of a C program and execution of a C program, and how this all works with so-called HPC environment tools that you really need in programming. So we will learn the module environment, that you need certain compilers, like basically for MPI, this library, to have this basically in as an example, or GNU, and so on. And with this, you basically start your baby steps of programming these large systems. Admittedly, again, a very simple lecture. Always think about that the usual lines of codes are really much more bigger. So starting with programming and compiling C programs, students usually ask the question, so why is that so important for HPC? Today we have JavaScript, we have Java, we have so many, let's say, Ruby and other, let's say, interesting languages, or Julia. So why in all we need basically C? So when you come to the idea of a HPC system, and those, of course, have high performance, so you want to use them in the most effective way. And traditionally, C was one of the most effective languages really to get the best performance out. Java actually is getting better and better in this, but still has the interpreter, right? Which is still, let's say, taking away some performance. And when you look into the overall domains, you see here the examples of the Jötunn Supercomputing Center with the simulation and data labs, from particle physics to neuroscience, including all sorts of different application areas in science and engineering. You will find mostly C programs, and in fact, also Fortran. With C, I also mean C++ programs, but there are even older programs, like, for instance, in neurosciences with weather forecasts or so, where Fortran codes are used. So let's say a much more perhaps traditional way of using programming languages with this, also thinking about that these codes maybe have grown over decades, right? I know, for instance, this Pathflow, what you see here as an example, to have a regional, let's say, forecast model, and you want to understand the water flow much more, you have maybe a subsurface water flow, you have the land, basically land cover model, which interacts then with the water into the subsurface, and then of course the atmosphere, and all of them run different codes, Cosmo, CLM, and Parflow. And we will actually look this and how it is coupled in one of our later lectures here. But the whole is basically written in C as one example here from the terrestrial systems. And then if you go to neuroscience with the Nest simulator, really understanding how a human brain works, a monkey brain, so it doesn't really matter. But it's also simulation kernel, which is written in C++. And hence, when you are working in the field of HPC and really want to understand also the parallelism here in the course, we have to take these examples. There's MPI for Pi these days, so Python also is on the horizon to be used, but still it's not really in the HPC community filling the systems yet. When you see the large system in high performance computing are still very much used with C, C++, and so on. So let's come to the more practical nature. We pick up what we learned basically in the last practical lecture 01. So of course we want to log in basically to our Jötunn system, and we learned there is a workaround with Graphical where we want to basically log in first. So when we do this, we basically go to our mobile Xterm, which I introduced as one interesting SSH client, but you don't have to use that one, right? So basically that's something where you're quite open to use the SSH client of your choice. And here you see now that we access Graphical as this kind of workaround, and then basically have the first jump inside the university network. Of course, if you are already inside the university network here on campus, maybe, then of course you can skip that step and go directly to Jötunn. But otherwise, you know, for me here being outside here and there, basically, then we also give you the idea how that works, or for remote students. And essentially, oops, you see here, Morris at jötunn.rhi.hi.is, and have to do again the password. And now I'm in. I increase here the font size a little bit. And you know, host name, yeah, the set is quite interesting to know. Okay, so we're really on Jötunn, and now we can start. So this was something you already learned, so no interesting news here, but it will be incredibly important always when you want to work on the assignments in the course. You basically have to log in, you have to work here on the system that makes it high performance computing. So this is just documenting what we have done before. Now, when we want to do C, obviously we want to write our first Hello World program. And again, the programming here and so on, it's not an emphasis on this course, right? We want to understand parallelism. We want to understand how to do parallel computing. For real proper C programming, Java programming, there are other courses in the university. So here and there, you will see that the kind of ideas of these codes are either very trivial, or I cut, let's say, beautiful other elements, which, you know, would be normally in the interaction with user, a good dialogue maybe or so. These are really core problems just to understand better parallelism. Here you see the simplest C program perhaps that you can find. You have this standard input-output library and these header files that you need to integrate for a typical C program. Usually this is something what you always need. Then you have this main program, really the main function that is then always executed when you start a C program. You can have different functions, more functions, obviously, but it's always called when you essentially use a C program. And printf basically says here that we want to have this string out, hello world, basically without a line break, which also means basically just the pure text will be given out. And is also often used for debugging, of course, you see program in the future in your assignments, so also quite an important command. And return 0 is usually used as basically an exit code. So you can basically find out how this was basically terminated, this you know, hello program. And basically non-zero exit codes like 1 usually means, for an example, that there was a problem, right? Or the program had to exit. When you do return 0, it usually means that was a normal run, no errors, we can just continue. And of course, there could be many of these ideas how you encode this, but this is a, let's say, modus operandi in basic C programming. However, the other aspect of a C program is that it needs compiling. And of course, now usually we do a hello.c as a naming convention in the course. In a way, you don't really have to do this, but I encourage you to do this. I would basically propose always to do this, to not get confused with executables, with things like that, because you're also not doing this daily. It might be that .c is a very good idea to basically use this. And of course, it remains a typical text file. So let's look how that could look like in practice when I go here into the Jötunn. So we're back on our system. We want to look where we are. So we're in my home directory. So let's have a look. Essentially, what is here installed, or what elements I have already. You see here all the different HPC courses in the past and NAIC workshops, and also our 2022 HPC course. So let's look into this. Again, remember the completion. When you press tab now, what I do, it will be completely this directory because there's nothing else starting with 2022, right? And when we go into this, of course, obviously, there should be something inside. And I prepared this here a little bit. We have MPI codes, which we can use here. So we want to have a look into these and see a little bit into this hierarchy of basically directories, which you see already here. Now we're not anymore in 2022 only, we're in MPI, hello. So basically have here our C program. And you see essentially what I had already on the slides. Here is our beautiful C program. Again, admittedly, very, very simple, trivial, but that's not the point. We want to understand firstly how we execute, and later then how we execute that on a HPC machine, right? That makes it okay to have it very simple. So we would assume that the output of this would be essentially a string saying hello world. So when we execute this, later we will basically see that. But of course, the first step we have to do is to actually then also compile this. And when we want to have MPI programs later, we basically need perhaps specific compilers for it. And so let's look a little bit what the software environment is if we say we want to have the basically the MPI programs later. We want to understand how we can compile such a C program. So you learned already in the last also that there is this module avail command, which shows you already all the different installed applications. You have here interesting different examples. One of it is the HPDB scan here in MPI and OpenMP. This is a clustering algorithm that you maybe can also look into. I basically gave you in the slides also the GitHub repository for it, right? Which is essentially doing clustering. And you see when you go here to the source and so on, that is the MPI and OpenMP program. So C in the sense of C++, and is basically from one of my older PhD students that already, who already was graduating. And by doing so, of course, this module environment should be consulted for the different compilers that you need, right? So this is, of course, something what the first thing is you have to understand, especially when you want to have, let's say, MPI programs, then you need to load specific modules in order to do something. You know, for instance, for us now, this compiling is incredibly important. When we to do this, here's an MPI-CC compiler, for instance, that we're going to use. And of course, before we use that, we have to load the right modules. And the right modules you can observe by doing this module avail. You also know module spider, essentially, right? I talked with you about this, that of course, this is also available. And for us, the MPI is basically an important standard that we're going to use in the first assignment and also in our subsequent lectures. To start early with the assignments, we will talk about MPI. Important is to understand, though, MPI as such is a standard, right? So that is not an implementation. There are many implementations of MPI. OpenMPI is an implementation of the MPI standard. Now, students can confuse that often with OpenMP, what I had the last time where I said OpenMP is shared memory program, also a standard for that. But here it's a big difference between OpenMP and OpenMPI. OpenMPI is really an implementation for the full MPI stack that we're going to use in the course, while OpenMP is used for shared memory programming only. So very important. And of course, for you is MPI not really obvious right now, and it doesn't have to be, because we will start with this in the next lecture and then in assignment 1 practically. But coming back to this module environment, it's perhaps interesting to see a little bit inside this HPDB scan if you have interest in and know a little bit of C++ programming. It's an open source tool which we use for doing clustering and high scales. Clustering means you want to have, let's say, data where, let's say, the different data points itself have no classes or no information except some similarity measure. Like here you see the Euclidean distance a little bit between those, which means that they are actually very close together and those are very close together and form perhaps a cluster. It's a typical data mining technique, machine learning technique. Here's a neuroscience application when you cut basically human brain into different slices and then want to analyze the cell density, which gives you different cortical functions in the human brain. Then you essentially can use such a tool to understand in each of these cuts a little bit, you know, where is this clustering, and with this clustering can basically then re-identify this cortical layers to some certain degree. There are some challenges, of course, when you dive into the detail, cells and so on, but it's not the point today. We will have a later lecture on neuroscience where we talk about this, and also about the parallel HPDB scan module much more in detail using parallel IO advanced techniques. Now here, just as a more simple example at the warm-up of the course, at the start of the course, here we want to perhaps use GNU 5.3.0 in order to use OpenMPI. So that means, in other words, basically whenever you want to use this OpenMPI, you get basically the information when you do module spider OpenMPI that basically this GNU is basically needed. So you have to load actually both of those modules if you want to create an MPI program. And an MPI program is basically a proper C program, and we will start with the C part today and have then a practical lecture 2.1, where I then go from the Hello World example to a real MPI program. And you will also see why we will then do this and what it entails to do parallel programming. So coming back to the idea now that we have this Hello C basically program in a typical text file, we now need to use a compiler to create basically an executable. And that's what we're going to use in the practical idea here. So coming back with clear, you can clear the space. It's sometimes good to work better with this and can list again all the files. Obviously, you see I pre-compiled that here, but when you go to vi hello.c and look inside, this is the same program we had before. And basically, as I showed you before I did this, just to check if it works and so on, with the arrow up, you see me now going through the history, what I did here. And when you do this long enough, you will see essentially the MPICC command that I used essentially for this compilation. Again, this was one tip of the practical lecture the last time, you remember. And you also see that before I did the compilation here, with MPICC, I load the proper modules. So module load GNU OpenMPI, preparing us for using OpenMPI in a later lecture. And then, of course, we can also here use now essentially the MPICC command. Of course, you can retype it. And of course, sometimes it may be even easier to do this. You see, I go here quite long through the history. But in many cases, you have the arrow up as a very good helper. So I encourage you to use that together with a tab. It's really time saving if you think about every interaction with your computer. So the MPICC now compiled this hello.c program, and this -o is just a naming convention. It says that the output of these compiling is a hello executable with this name. You don't have to do this again. It's basically optional, but it helps a little bit to really understand, you know, that this is now a complete different part from hello C. And you notice this firstly here, not only from the size of the hello program, which is this executable here marked in green, you also see essentially this X for executable through all the writes of the file. So this is something which we really can execute in order to provide output. And obviously we want to do this, test this, and would think, okay, now we do hello dot, not anymore dot C, we just have hello, and we'll execute this. And you see here, beautifully enough, we have the hello world given out. And of course, now arrow up means I can repeat this step beautifully many times, but I think you already get the message that this is quite nice. And now you would say, we have done this all and we are very, let's say, happy about this. But in a way, what we did was a little bit not so good. And I will come to the point. Obviously, it's needed that we compile a program on the so-called login node, right? And we are now in Jötunn. And I'll show you in the scheduling a little bit more about Jötunn, the situation, how it is basically running and so on. But let's go and look a little bit more what practical views we have now. So it's best explained by looking up what your system is. Here we go to the Jötunn system on the EHPC National Competence Center side. And look, it has 4 nodes, which is not completely true because we'll also see we have 4 nodes plus 1. And this plus 1 node is the so-called login node, which is always usually actually in these HPC production systems there, even here with a teaching cluster. And when you go to the site, you have something called ganglia, which I also will basically show you then in the second part of the lecture. And now you can see the load. And of course, obviously in all the different, you can choose a node here on the Jötunn cluster, where you basically have this Jötunn as login node and then the different compute nodes, right? Where you see essentially what's happening. Obviously, we also see that the course is just starting, and as a teaching cluster, not many use this basically system. So in a way, it's my teaching cluster here. And with this, you see a little bit about statistics throughout the course. So you can use this in the course to understand a bit what the load is. You will see once we have greater assignments, when you come to deadlines of assignments, that this load will be, of course, suddenly increased. And with this, you may become even in the trouble that basically others are using the system and there's no free space for you. But this will be part of the second part of this lecture today, understanding scheduling a bit. The point here I want to take away is it has obviously 4 nodes and a login node. So what's now the dependency of running jobs and what we just did with the compiling? So in other words, we have to think about that this step, what we just did was perhaps very good. But when you now look on the full situation that I executed, actually this program on the login node, on this Jötunn node, this is not how you usually do it in HPC. And here are some older administrators from us and Hjörleifur, who is still an administrator in HPC. We always were, before COVID-19, obviously going to these clusters and touch metal, as I call it. So by now you would have seen already a real HPC system. We have to think hopefully that this can be done a little bit later in the course when COVID-19 numbers are reduced. But essentially these gentlemen will come to you or call you if you use this too much, this feature of just executing on the login node. Firstly, it is not as powerful as using the other nodes. And here, of course, we have not 6, we have 4 nodes. So this is just, let's say, a general graphic. But we just learned from the overview that we actually have 4 nodes to use. And we use the Jötunn login nodes actually then for the hello world and to basically execute it. So for compiling, this is a normal modus operandi. You would say the login node can be used for many things, statistics here and there, if it's light statistics, some modification, programming here and there. And of course, as we've seen, the kind of idea of really going a little bit about the compiling, understanding the module environment, experimenting here and there with the module environment, looking up information. You can do a lot of things with a login node. But basically what we're really interested in HPC is then the compute nodes. And once you use them in other course parts, the accelerators, the GPUs, which are attached to such nodes, not for Jötunn here, but for the deep system, for instance, then you will notice that even a GPU code doesn't work really on the login node, obviously, because it has no accelerator usually, because we don't want to use it. It's just for hopping on it with SSH, being there, being logged in, and then use it for, let's say, more trivial tasks. and so on, and to work with the system. When we go full-blown production, a real application run, then we want to do this via a so-called scheduler. And the scheduler will basically put your job somewhere here. But this is basically the part of the next lecture. And that's why I basically want to stop here in a way, because the second part of the lecture today will really looking into this. We'll basically look a little bit where we are in terms of placing different programs really from this Jötunn system, basically understanding also then what happens if not me alone is logged in. What about if, let's say, you with 40 people in the course, for example, or more at the same time are logged in, and all of you actually then will use a scheduler and will use a Jötunn. So obviously, we see here in the overview of Jötunn, if you look at it, it is basically older, of course, which is not a problem for our course because we have, let's say, basic MPI programming here and basic parallel programming. But we see with 12 cores and 4 nodes, somewhere there is a limit, right? And this limit means that when more and more students use it at the same time, and we come to more complex assignments like assignment 3, where you do a bit more, then you basically have the question that not everybody has space right now. So you put in the queue. And this is, of course, the core challenge here. What we basically have to understand that this is a multi-user system, and essentially saying that, we have here to look always what the other users are doing. And basically in subsequent, times in the course where you have the assignments and so on, you also see then the different, let's say, usage of these systems go up. And with this have also information that your basically other friends in the course, the other students in the course are all computing. And there are different ways how you can do statistics here. I think obviously you can have from times, switch to different nodes here or have an aggregated overview, basically, where you can see that basically the overall usage from the CPUs in the last hour is very low because we're just starting the course. And with this, of course, have not really computed much. And the hello world that I just executed is almost negligible in the overall runtime. And that's why basically this gives just a very little footprint in the overall use of the system. And yeah, essentially, you see that the user already starts it with 0.1%. That might be actually myself. It's not idle, the 99.7%, and this 0.1% could be exactly what I just did here with the kind of compiling a little bit and executing a little bit on this Jötunn. But in subsequent basically lectures and then in our Q&A session, we can review again the Jötunn system. We will see it's much more heavily basically used by all the different students and student groups, what you should do also basically as an assignment. And with this, I'm done for the first part of the lecture. As I said, there's still not the full picture. We will basically learn how to do it better with the so-called submission batch scripts and scheduling. So stay on and join us for the second part of the lecture.